Okay, we have the same announcements as last time. Programming assignment 1 is still due. There's still videos. But today's plan has changed. Today we're going to be doing linked lists, and we'll talk about a stack abstract data type if we make it there. And just, so this is like a warm-up slide. This slide has the structure that we talked about last time, the node structure that was part of the linked list. And you'll see that in this node structure, not only does each node contain some data, which is templated to be of type lit, could be an int, could be a string. It also has a pointer to another node structure. So that's the linking that's happening in this linked list. The next field takes you to the next node in the list. And then the final thing there is a constructor, which, given some data and given a pointer, creates a new node that has that data as its data field and that pointer as its next field. Okay, that's what we did last time. We talked about that last time. And so now we're going to do some operations on these linked lists. We're going to go over how to write code to manipulate these things. And the first thing that we'll do is figure out how to insert something at the front of the linked list. So this is the insert at front call. Here is the list prior to the call, before the code is called. Here's the call. And here's what it's supposed to look like after the call. See, it puts another node at the beginning, insert at front, puts another node at the beginning. Okay, so that's the template for the function, and you're going to figure out what code to add here, where it says add code here. But before we do that, before you do that, I want to ask you a question. What the heck is that? That's part of the signature for the function. The function call takes two parameters. One is called cur and one is called e. But cur's type is node star ampersand. Yes.
You're pointing at the node, and then you use the pass-by to change it.
Okay, so excellent. So the type of that cur is a node pointer, but it's being passed by reference. So that's what this little ampersand is doing. So the way to read this is it's a node pointer passed by reference called cur. Yes?
Also, the difference between passing a pointer by value and passing a pointer by reference is that in passing by value, you make a copy of the pointer and then pass that in.
Correct. You're just passing a pointer by value, or in the normal way, if I just said node star cur, then you would just make a copy of that pointer, whatever value it is. It's some 0x007 times, one big long address. Or make a copy of it and then call the code.
So this is like the original pointer that we're passing, essentially.
This is the reference to the pointer in the caller's frame. So the caller of this function, this person that wrote down insert at head cow, wants head to be changed. They want the output to no longer have head pointing to dog. They want head to point to cow, the new beginning of the list. And in order to do that, we have to allow the function that we're calling, that is insert at front, we have to allow that function to manipulate the pointer in the caller's frame of reference, and that's why we need to pass the parameter as a reference parameter. Then the manipulation that's being done in this line of code that you have to put there, you have to figure out what it is, will change the caller, change head in the caller's frame. Is it good? Okay, so now you understand what this thing does and what the signature is. Now I'm going to give you 1 minute to figure out what line of code should be put here. And I will tell you it's one line. So you have a minute, go. Yeah.
Will your slide be up on the website?
Which slide?
Oh, this slide.
Oh, those slides? No. Should I put them up? Okay, I'll put them up. You're getting an extra minute. Okay. Has everybody figured this out? Now that you have to wait a little bit. It'll eventually, the slides should show up on the website soon. What's the line of code that I put here? Anybody want to conjecture what line of code I put here? Yes.
Star car equals
Star what?
car
Okay.
equals node e car.
Star cur equals node e cur. So the node e cur is going to call it the constructor, and it will create a new node. And where will it create that new node? What memory will it use to do that? The stack. So now it then sets star cur to be that node, and then it returns. And what will happen to the memory that was on the stack when that return happens? It will get blown away.
So should it be new node?
Yes, there should be a new in there. For sure, a new. So let me put a new in the front. So remember, new is allocating memory that's permanent, so it will last beyond the lifetime of the function that you're calling, with the context of the caller, of the callee, this function here. And so new is going to allocate memory. It's going to ask for memory for a new node with data e and with a next pointer that's current, and it will return to you a pointer to that data. So now what do I write? This is equal to nobody? Yes. What do you want to call it? Just what am I going to write here? Wow, that was like dogs could do that. Like really high pitched. Anybody want to fill in the blank? Yes. Kirk. Anybody think this is a little bit peculiar? Everybody happy with this? Cur indeed is a pointer. It's a node pointer, so it's not like you're doing something bad by making cur equal to new node e comma cur. But the question really is, what happens when that assignment occurs? So cur gets set to be this new pointer, but cur was passed by reference. So the actual value that gets changed is the caller's value that was passed, which is head. So this call right here included a head, and that variable, that's the one that gets changed. So this assignment here changes the value in the caller and updates our head value to be the pointer that's returned from this new node call, the thing that allocated memory. So this works. This is it. This is the one line. It's kind of slippery. It's kind of sneaky. It's not changing just cur. It's not changing just a local variable. It's changing something that's in the caller. That's what happens when you use reference parameters. Yeah.
So if you call new node, doesn't that return node and not a pointer to a node?
No, new node returns a pointer to a node. New is a function that it takes a structure as an argument and it returns a pointer to the memory required to hold that structure. Any other questions about this? Don't worry, you'll get more chances to ask questions because we're going to talk about reference parameters again, and then again, and then eventually we'll stop talking about them. But for now, we're not done yet. Yeah?
In this case, cur would just be a node pointer to that new node that we created. But how does that allow us to add that node to the existing linked list?
What is the way in which the C programming language parses that line of code? What does it do in order to figure out the operations involved in that line of code? You know? But it starts on the right-hand side. It has to figure out what thing it's actually going to come, what thing it's going to give to the left-hand side. So it starts on the right-hand side of the equality sign, and it tries to figure out what that is. Well, in order to figure out what is on that right-hand side, it has to actually know what cur is. So it evaluates cur. Cur happens to have a value which is the old head it was passed in. It evaluates e, also something that was passed in. Now it knows what to pass to node, so it passes that to constructor. The constructor constructs something, returns a pointer, because new is the thing that's calling it, and then there you go.
So is the node constructor the actual function that's attaching that new node to the list?
No. I mean, it's a combination of things here. First of all, we're passing in the current head as cur, so that into the node constructor. So it's using that to be the next pointer of some new node that it's building. But then we're also assigning whatever that pointer is that we get back from new, we're assigning cur to be equal to that. And cur is a proxy. It's like a way to modify the actual original head pointer. So that's how we're adding it to the list. Because the head is getting updated by that assignment, and the pass into the constructor is giving you the extra links going on. Okay? We'll see more of this right now. Not right now. Here's another exercise for you to do. Print the odd locations, the contents of the odd locations, in reverse order. Now you might think to yourself, what are the odd locations in the linked list? And I'm going to define the odd locations as being these ones. And you might say, wait a minute, doesn't C index things from 0? Shouldn't that first thing be an even location? And I will say to you, C is not the only programming language in the world. There are many other programming languages, and they actually index from 1. And when you're indexing a linked list, at least on this slide, in this class, it's starting at 1. We could have started at 5, but we started at 1. Okay, so does everybody understand what this does? So if everybody understands what this does, everybody tell me, what does this print? Which way is reverse order? This is the head of the linked list, so regular order is from head to tail. So reverse is that way, the other way. So what does this print? Go ahead, you can say, thank you, 5, 2, 8. Excellent. So you can write your line of codes, or lines of code. How many lines of code did I use? I needed, okay, technically I needed 4, but really, you only need 2. Really. Because you have to check certain things, right? I mean, let's think about how we're going to do this before everybody starts writing. It's always a good idea to think about how you might construct this code. So we want to print this thing in reverse order. So how are we going to do that? The first thing that has to come out is the last odd location. So somehow it would be really cool if we could figure out a way to do this recursively, right? It'd be great if we could figure out how to say, for example, let's look at the list and let's just forget about the first part of it and print the odd things, and maybe forget about the first 2 things and print a reversed version of what remains. That would be the first part, the 5 and the 2. And then all we have to do is, after that recursive call, then all we have to do is print out 8, the front. So if you like recursion, and you really should, this is perfect for recursion. You just have to have a recursive call do the work for what remains down there, and then when we come back from that recursive call, we do the last print. Does that make sense? recursion. Trust the recursion? You remember that? This is one of those situations where you want to write code that trusts the recursion to do the right job, and then make sure if it does the right job, what you do in addition finishes the job. So I'll give you 30 seconds to do, well, I'll start writing. And you can write your stuff while I'm writing my stuff. You're watching. How come you're not writing your own? Should I put a bug in the code? Yeah. Everybody figures something out? So let's look at what I wrote, because something's wrong in what I wrote, but it's good to know what, at least the first part is something that seems needed. So if the current thing, if it's null, we don't have anything to do, right? If the current pointer is null, then there's no list to reverse, and we're done. And not only that, but if the next thing, current pointer to next, is null, then we're done, because there's nothing more to do. We have to peel off the first two nodes in order to make the recursive call, and there are no two nodes to peel off in order to make the recursive call. So after we check that current is not null and current doesn't point to something that's null, then we make the recursive call on current. By the way, this is originally called with head as being current. Oh, and here's another question. Sorry to distract you, but why in the world don't I have this passed as a reference? Could I pass it as a reference? Why did I not pass it as a reference? Wait, who said that? Who said that? You did? Oh. I don't want to change the original. Actually, what I'm doing here in this signature here is I'm saying I am not going to change the original. Right? It's not being passed by reference, therefore whatever happens, whatever value is getting passed in is being passed by value. And so if I monkey around with that value inside of this code, you, as the person calling this code, are confident that I won't be messing up the pointer that you give to me. It won't change. So it's a little bit of information to you using this code that I'm not going to touch it. Now I could be even more explicit and put a const in here, but frankly I always get confused using consts. So I didn't put that in there. Const is like a promise that says I'm not going to change it, but this is like a hint that says even if I do change it, it's not going to matter to you because it's not passed by reference. It's just a pointer that's been copied. And I don't need to change it because I'm not manipulating, I'm not changing the list. All I'm doing is printing it in a weird order. Okay, so back to our story. So now we do this check to make sure nothing's null. And then we print we do the recursive call. And we know that this chain of pointer followings, curve, pointing to next, is a valid thing to do because we've checked the cur is not null, and we've checked the cur pointer to next is not null. So I am not dereferencing a null pointer, so I will not get a segmentation fault, and my core will not die, at least for that line. Yes?
Wait, when you print like cur arrow data, can't that be a set fault? Because you don't know if this cur might be at all.
Are you jumping ahead to the next line? Okay, good for you. That's good. Is everybody else done with the first two lines? You're okay? You have a question?
No.
You're okay. Everybody's okay? Okay. Now, go. Say what's wrong.
Because like, yeah, sure, the recursive call works with curve on null, next one on null, but that curve might be null, and then when you try to print the data, then it's the next one.
Yeah, so this code has a bug in it because when I try to print this data, what's to say that cur isn't null? So that's the thing that I left out, and you found it immediately. So you're very clever. If cur is not equal to null, that just means I'm going to make things harder in the future. If cur is not equal to null, then we see out cur pointer to data. Yeah. How does it work? Pardon me? Print the locations in reverse order. So you're worried about the order in which the print is going to happen? So let's try it. We start off here at the top. The current location is pointing to 8. And when we make this call, what it does is it prints recursively this in reverse order. Now you believe that that works, I hope. Do you believe this works? Okay, so then it prints out 5 and it prints out 2. And then it falls out of that print, and it says if current's not null, which it's not null, then it prints out the data. So then it prints out 8. So I think it works. I mean, you might have a nitpicky detail here, which is that, well, I want a carriage return at the end of the 8. And then I say, too bad. You can't have that. You can have that if you let me write a helper function. So, but anyway. Is it okay? This is like refresher also of recursion. What's the running time of this code? Okay, I'll tell you. Meaning I'm going to tell you the parameter. I'm not going to tell you the answer. The parameter is n, which is equal to the length of the linked list. Now, what's the running time? Just guess. I missed it. Somebody said something. Yeah.
Will it be log 10 such you're only going through half of those?
If I'm only going through half of them, it should be n over 2.
Yeah, which becomes full of n,
Right. So, O or n? Everybody happy with O or n? How did you get that? Yeah.
Isn't it current less than?
You want it to be 2 times n?
Well, not quite.
2.5 times n?
Yes.
1.5 times n?
Yeah, I think that's.
You think 1.5 times n? Okay.
Yeah.
You know what's so nice about big O notation? I don't have to worry about that. But I do have to worry about it if I'm actually trying to calculate the function, which is the running time. Suppose t of n is the running time. Suppose that I wasn't able to say immediately that this is big O of n. But all of you seem to accept that this was big O of n. But it's kind of weird because it's a recursive function, right? So t of n, if this is the running time for size n, what this code does, is it starts off, so t of n is equal to, it starts off by performing some operations, and then it reduces the problem to a problem of size n minus 2. So t of n is actually equal to something like maybe, let's say maybe 2. Oops, come back. I mean, I don't know what you want, but I'm going to say it's 2. 2 plus t of n minus 2. That's what the running time is of size n. Now, of course, this is a recursive program that eventually terminates. In fact, there's a base case for this program. We know that when cur is null, so when the size of the array is 0, we know that it really just basically does 2 steps. And when the array is of size 1, that is when cur pointer to next is null, then it also basically does just 2 units of work. So we have base cases for the runtime too. And now, what do we have here? This is a set of equations that's forming a recursive definition for our running time t of n. And somehow you are able to automatically convert this into a function that's big O of n. Because you understand how this works. Somehow you've understood the unraveling that's going on in this recursion without actually having to solve this recurrence relation. This is a recurrence relation, by the way. And that's totally cool. But I have to tell you that it gets harder. This is one of the easier recurrence relations. Right? You sort of see what's going on. You can sort of say, oh, I can look and see, let's see, t of 3 is going to be 2 plus t of 1, which is, whoops, I skipped 2. Let's do t of 2. T of 2 is 2 plus t of 0, which is going to be 2 plus 4. And t of 3 is going to be 2 plus t of 1, and t of 1 is 2, so it's going to be also 4. So you can play with this, and you can do a few examples for larger and larger values of n, and you can look for pattern. And that's basically one way to solve recurrence relations, is look for patterns. This is a pattern which is saying every 2 steps it's going up by 2. And so from this you can get that t of n is something like the ceiling of n plus 1 over 2 times 2, which is big O of n. Okay? We will see recurrence relations again. This is just the easiest recurrence relation that we'll probably ever see. Okay. Any other questions about this? Yep.
Where'd you get that good 2 from? Is that just counting lines?
Yeah. I just said there were 2 lines here.
What did I do before?
Okay. If you want 4, change this to 4. I had 2 lines. I originally had 2 lines and they were long lines. And then I realized that I wouldn't be able to write them onto the slide, so then they turned into 4 lines. But really they're just 2 lines. Sorry. Any other questions about this? Okay. Next. Reverse the linked list. So you give me this linked list with a head pointing to 8, and I want to reverse it. And so that means that what should happen to the linked list is that after this call, head should point to a new linked list. Well, not a brand new linked list, the same linked list, but rearranged so that head is now pointing to 3, and 3 points to 5, and 5 points to 6, and 6 points to 2, and 2 points to 4, and 4 points to 8. It's backwards. It reverses the whole thing. Okay? This one is changing the head pointer that's been passed in, so that's why the current pointer is passed by reference. And there will be changes to that inside the code, yeah?
I think I remember I heard somewhere that it passed the parameter as a pointer, that it's also passed by reference, right?
Yes.
So in the previous slide, aren't you also passing by reference since you're passing it as a pointer?
What am I passing a reference to if I'm passing in that pointer? So in the previous slide, I'm not passing a reference. You shouldn't think of it that way. You should think of it as being the address. You're passing the address of something, and that's a pointer, or you're passing a reference to something, and that's implemented in C++ as if you passed a pointer to it, but it's not allowing you certain operations that you can perform as you could on other pointers. So it's weaker. But anyway, this is a pointer to current. So if you wanted to interpret it as a reference, it's a reference to an object, current. It's not a reference to a pointer. It's a reference to an object. This is a reference to a pointer, and so it's changing a pointer, not an object. So we could, in this code here, we could say current arrow data equals, I don't know, sorry, I was evil there for a second because I just erased your data, right? I can use this pointer to erase the data inside of the node that's pointed to by current. So it's a reference, it's a stronger thing actually than a reference to that object. Here, we're just saying it's a reference, so we can't do really crazy things. There's other crazy things we can do, but this one, all we can do is change that value to something else. But you're right, you can mimic this by passing in a node star star. But then you have to dereference everything when you're complicated. Okay, all right, so we want to reverse this. What do you think we're going to use to do this? What programming paradigm? Recursion. Right. Like, I suppose that at some point in the code, we would say, let's reverse everything after the head. Okay. And if you trust the recursion, then what will happen is we'll end up with something that looks like this. 3, which points to 5, which points to 6, which points to 2, which points to 4, which points to nothing. That's the recursive call that, actually, let me just write it down. The recursive call, okay, I have to do some checking here. I'm going to write something down. Hold on just a second. We have the same sort of checks that we're performing as we did before, because if I have only one element in the array, or if I have no elements, or if I only have one element in the array, we don't have to do anything. Right, because the reverse of something that only has one element in it is just the same thing. We don't have to do a thing. So if they have more than one element, if they have 2 elements in it, for example, then what we'll do is we'll create a new local value called t, which is a node pointer, and we'll use it to stash away the next field of the current node. Okay, and then there's a recursive call. So then there's this call, which is reverse, just exactly what you would expect. Current pointer to next. And that's supposed to work recursively. We just believe that it works. Okay, so what this recursive call does is it reverses the list, just like I've shown up above. But it does one other sneaky thing. What's the other sneaky thing that it does? Because of the pass by reference. This call. What? Now what? Let's see if I can make it. Wow. This right here is passed by reference. That's right, reference. It's passed by reference. What does that mean? That means when this reverse occurs, what is current pointer to next going to be? See, originally this was current. And this right here is current pointer to next. And we passed that pointer, this one right here, we passed that one into this function right here. And when we did the recursive call, it changed that value. So this value now points to 3. It used to point to 4, but now it points to 3. Because this pointer, the one that's in red that I keep scribbling on, that pointer is the one that's updated by the recursive call. Current pointer to next is a reference parameter. It gets updated by that function call. Okay? Is everybody okay with this? Because this is what happens in structures where you pass pointers around as references. This structure, this linked list structure, can get torn apart and reconfigured simply because you're changing the value that you've passed into a call. So this value, current pointer to next, because I passed it in as a reference parameter, it can be modified. And so in fact, that particular value, the one that's in the structure, the one that's in that first node 8, gets modified. And it gets updated to be the start of the reversed tail of the list. That is the start of 3, 5, 6, 2, 4. So if you trust the recursion, this is what happens after the recursive call. Which is why we stashed away the current pointer to next. Before we made that call, we stashed it away into something called T. So this is T before we made the call. Right? It pointed to the node that contains 4. So we didn't lose that. And in fact, T is still pointing to the node that contains 4 once we've reshuffled everything, because we don't change the pointers, we just reshuffle the way in which they're linked together. So this T value is a pointer to 4. I feel like I have to pause and ask how many people are confused at this point. Okay. How many people are not confused at this point? That's not so good. Let's go through this again with different words. You understand that the original parameter that passed to this code, reverse, is a reference parameter. So whatever you pass, if this modifies it, and I haven't shown you the whole code, so maybe that would help. Should I show you the whole thing, and maybe then you would see the whole picture? Because this isn't the end. It's not the end. T pointer to next equals null. Current equals current pointer to next. That's next. And then the last thing is the weirdest one. T pointer to next equals null. So So that's all the code. So let's walk through all the code and we'll see what's going on. So first of all, we're checking to see whether we're done. And just think about it as being starting at 8. We're not done yet. So we're not done, we're not even close to done, right? The length of this linked list is much more than just one thing. So it's checked current, no, it's not null. Current pointer to next, no, that's not null. And so then it says, I will set t to be current pointer to next. So this is what it does. This line right here, line number 1, is what sets up this, and it's what sets up that. Okay? That's all it does. Just makes another copy of a pointer to that particular node. Then there's the reverse call. Let's just believe that that works, and it reverses the linked list. So I get a new linked list that looks like 3, 5, 6, 2, 4, and then 4 points to null. That's great, but in addition to that, it must modify the parameter that it's been given in order to make that parameter point to the new head of the reverse list. So that parameter that it's been given in this call is cur arrow next, which is designating a specific pointer. It's this pointer right here, the one in the red blob that I keep scribbling again and again and again. But it's that big red dot. That is the pointer, the one right there, that gets changed. And so at the end of this step here, the picture looks like this. We have t pointing to 4. We have cur pointing to 8. We have the cur pointer to next pointing to 3. And then we have this sequence of linked lists, this linked list. That's what happens after this recursive call. Now we have to fix things up so they actually are the thing that we want. So let's change colors because that will make things easier. Blue. So this is post recursive call. Post recursive call, the first thing that we do is we set t pointer to next to null. This is t. No. No. Sorry. That makes no sense. T pointer to next equals current. Oh, that makes things a lot. That's exactly what I was waiting for. Yeah, the problem is I have new glasses, so I can see you, but I can't read my notes. So I just sort of guess. And I guessed wrong. So t pointer to next equals current. So let's see, t pointer to next is currently null, which was my tip-off that I probably copied my notes wrong. So we actually make this pointer right here, which is t pointer to next, the next pointer here, we change it. Oh, right, I'm supposed to be blue. Blue. We change this so it now points back to current. Now, there. Okay, that's what this line does. The next thing that happens is we set current to be current pointer to next. So this line of code here, which I'll do in green, this line here is going to update the value current, which is this parameter that's been passed by reference. So it's really modifying the head. It's killing the head here, and it's making the head point to current pointer to next, which also kills current. It sets it to be here. So this becomes current, which in fact in this frame is also a reference to head. So head changes and current changes just from this line. Okay? So now we've got this weird looking linked list. It starts off with, I gotta follow the right pointers. This big red blob is the right pointer to follow. This is the new value for current, which is also a proxy for head. Sorry, that's the last mistake I will make today. Okay? And now, after the green line, we have a linked list that starts off at 3, and you go to 5, and you go to 6, and you go to 2, and you go to 4, and 4 takes you back to 8, and 8 takes you to 3, and then you go to 5, and then you go to 6, and then you go to 2, and then you go... It's a circular linked list at this point. We don't want a circular linked list. We got to kill it. So we kill it by doing we kill the last link by, in not yellow, but something like magenta, we kill that by that line. We use T, pointer to next, follow the blue line, pointer to next, follow the red line. This thing we kill. So this kills this link. It sets it to null. And we've now reversed the entire list. I'll see you next time, Friday, for more fun with, well, only a little bit more fun with pointers.